For this week, we focus on 5 parts: basic terminology in petroleum engineering, the structure of the petroleum industry, current industry status, a basic introduction to carbon capture and storage, and then a recap with what comes next. This week is especially important because it builds the vocabulary and conceptual map you will use throughout the course. Let's start with a simple question. When you hear the word petroleum, what comes to mind? Many people think first of gasoline or diesel. Others think of transportation, energy, or pollution. But petroleum is much broader than fuel. It is connected to everyday products such as plastics, synthetic rubber, detergents, personal care products, and many industrial materials. So in this course, I want you to think of petroleum not only as fuel, but as a major part of the modern materials and energy system. To understand petroleum, it is useful to start with the word itself. The prefix petro comes from the Latin and Greek root related to rock or stone. This is why I show Petra in Jordan, the famous rock-cut historical site. It helps us visually remember that petroleum is strongly associated with rock formations underground. In petroleum engineering, geology matters because petroleum is generated, stored, and trapped in rocks, not in empty underground caves as many people imagine. The second part of the word petroleum comes from oleum, meaning oil. So if we combine the two roots, we get the idea of rock oil. This simple word origin already tells us something very important. Petroleum is an oil-like natural substance associated with rock layers beneath the Earth's surface. Understanding terminology helps because petroleum engineering uses many specialized words, and many of them have geological or historical origins. Here we combine the two parts, petra meaning rock, and oleum meaning oil. Petroleum literally means rock oil. This is a useful definition to remember because it connects language with geology. Petroleum forms from organic matter over geological time and becomes stored in rock formations. If you remember only one thing from these first slides, remember this: petroleum is not just a commercial product, it is a geological resource. In engineering practice, petroleum is defined as a naturally occurring mixture composed predominantly of hydrocarbons, and it can exist in gaseous, liquid, or even semi-solid phases. This includes crude oil, natural gas liquids, and condensate. These are all petroleum-related fluids, but they differ in composition, phase behavior, and how we produce and process them. As we move through this course, we will become more precise about these categories because they strongly affect field development strategy. Petroleum is mainly made of hydrocarbons, which are molecules made of carbon and hydrogen atoms. A simple hydrocarbon family can be represented by formulas like CnH2n+2, especially for alkanes. The structure and size of hydrocarbon molecules strongly influence fluid properties. Smaller molecules tend to form gases, while larger and more complex molecules tend to form liquids or heavier fractions. This is why chemistry matters in petroleum engineering. Chemistry influences flow behavior, production strategy, and refining outcomes. Crude oil is not always black. Its color can vary from light yellowish to dark brown or black depending on composition and impurities. In practice, engineers often use API gravity to describe how heavy or light crude oil is. A higher API gravity means a lighter oil, and generally lighter oils are easier to process and often more valuable in many refining contexts. So when you hear someone describe a crude as light or heavy, they are usually referring to density-related properties, not just color. One of the first unit systems you must become comfortable with in petroleum engineering is oil volume units. The most common industry unit is the barrel, abbreviated as BBL. One barrel is approximately 159 liters, or about 0.159 cubic meters. In the other direction, 1 cubic meter is about 6.29 barrels. Please remember these conversions because you will see production rates, reserves, and economic calculations reported in different unit systems depending on the country or software. Let's do a quick knowledge check. How much oil do you think the world consumes per day? 12 million barrels, 55 million barrels, or 97 million barrels? The purpose of this question is not only to test your knowledge, but to help you appreciate the scale of the petroleum industry. Even if you guessed incorrectly, that's okay. The key takeaway is that global oil consumption is enormous and deeply connected to transportation, industry, and modern supply chains. The answer is C. For natural gas, a common industry unit is standard cubic feet, or SCF. The word standard is important because gas volume changes with pressure and temperature. At standard conditions, 1 SCF is approximately 0.0283 cubic meters. In petroleum and gas engineering, unit consistency is critical. If you mix reservoir condition volumes, standard condition volumes, and surface condition volumes without conversion, your calculations can become very wrong. This slide introduces the basic story of oil and gas formation. Ancient marine organisms and organic materials settled in sediments, were buried over millions of years, and then experienced increasing heat and pressure. Over geological time, these conditions transformed the organic matter into hydrocarbons. Later, those hydrocarbons migrated and accumulated in suitable rock formations. So petroleum engineering begins long before drilling. It begins with Earth history, sedimentation, and geologic processes. Now let's move from formation to accumulation. This slide asks a very important question. What roles do source rock, reservoir rock, and cap rock play in creating a producible petroleum system? These three rock types are central to petroleum geology and exploration. If one component is missing or ineffective, large hydrocarbon accumulations are much less likely to die. In the next slide, we will answer this directly. Here is the key concept. Source rock is where hydrocarbons are generated from organic matter under suitable temperature and pressure conditions. Reservoir rock is where hydrocarbons accumulate. It must have enough porosity to store fluids and enough permeability to allow fluids to flow. Cap rock is the sealing rock that prevents upward leakage, trapping hydrocarbons below it. When these elements come together with proper timing and migration pathways, we get a petroleum system capable of forming economically recoverable oil or gas fields. Next, an important drilling and reservoir term, the geopressure gradient. This describes how pore pressure changes with depth, often expressed in psi per foot or kilopascals per meter. A normal hydrostatic gradient is often used as a reference. If actual pressure is much higher than expected, we may have overpressure, which can create serious drilling hazards if not managed properly. Understanding pressure gradients helps engineers choose mud weight, casing design, and safe drilling procedures. Maturation describes how a source rock becomes capable of generating oil and gas under appropriate temperature, pressure, and time. As maturity increases, the hydrocarbon products can evolve from heavier oils toward lighter oils, condensates, and eventually dry gas at higher temperatures. This concept is essential for exploration because it helps us estimate whether a source rock in a given basin is immature, oil-prone, or gas-prone. It is also especially important in shale systems, where the rock may act as both source and reservoir. The geothermal gradient is the rate at which temperature increases with depth in the earth. Near the surface, a common value is around 25 to 30 degrees Celsius per kilometer, although it varies by region. This matters because source rock maturation depends strongly on temperature. So geothermal gradient helps us estimate wherein the subsurface oil or gas generation is likely to occur, and how basin thermal history influences hydrocarbon type. This slide brings together kerogen, geothermal gradient, and pressure conditions to explain the oil and gas window. Kerogen is the solid organic precursor in sedimentary rocks. As burial depth and temperature increase, kerogen transforms first toward oil generation and then toward wet gas and dry gas. The oil window and gas window are not just abstract concepts, they help exploration teams predict what type of hydrocarbons may be present before drilling. Now let's apply what we learned using a simple exercise. We are given an oil sample with specific gravity of 0.95, and we are asked to estimate API gravity and identify the fluid type. This exercise is useful because petroleum engineering often combines basic property calculations with practical classification decisions. Now we transition from petroleum basics to the engineering workflow. How do we actually find oil and gas in the subsurface? Finding hydrocarbons is a multidisciplinary process that combines geology, geophysics, drilling, data interpretation, and risk assessment. In the next few slides, we will build a simple mental model of this workflow. This slide emphasizes that petroleum engineering is not only about production after discovery, it also plays a major role in evaluating whether a discovery can be developed safely and economically. Geologists and geophysicists help identify possible reservoirs, while petroleum engineers assess rock and fluid behavior, well performance, and recovery strategy. The key point is collaboration. No single discipline can deliver a successful petroleum project alone. Here we introduce the life cycle of a hydrocarbon field: exploration, development, production, and abandonment. In exploration, we identify and test potential subsurface resources. In development, we design wells and facilities. In production, we operate the field, monitor performance, and optimize recovery. In abandonment, we plug wells, decommission infrastructure, and restore the site. This life cycle thinking is very important because good engineering decisions should consider the full project timeline, not only short-term production. Oil production generally progresses through 3 recovery stages. Primary recovery uses natural reservoir energy, such as pressure drive, to bring fluids to the surface. Secondary recovery injects water or gas to maintain pressure and improve displacement. Tertiary recovery or enhanced oil recovery uses methods such as chemicals, heat, or CO2 injection to recover additional oil that remains trapped after earlier stages. This staged view helps students understand why reservoir management becomes increasingly complex over time. Let's do another practical exercise. The original oil in place is 5 million barrels, and analogous fields suggest recovery between 70 and 90%. We estimate a lower and upper recovery range by multiplying the OOIP by those recovery factors. This type of calculation is basic but very important because early field decisions often begin with range estimates, not exact values. Engineers must think in terms of uncertainty. 2 estimates are possible, a lower estimate and an upper estimate. The lower estimate of oil recovery is 0.70 times 5 equals 3.5 million bbl. The upper estimate of oil recovery is 0.90 times 5 is equal to 4.5 million bbl. This slide introduces the idea of reservoir management and recovery efficiency. Modern reservoir management is not a one-time design task. It is a continuous process of monitoring, updating models, and optimizing controls such as injection rates and bottom hole pressures. The broader lesson here is that petroleum engineering is increasingly data-driven. We observe, update, simulate, decide, and repeat.